And he just posted up the information.
Well, I will begin with a word of prayer. So, dear Father, we thank you for this day again. I thank you for this class and this opportunity we have to meet and study your creation. Just pray that you would again be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. So do you guys have any questions about anything in particular? Yes, no, maybe so, no. So I'm sorry I haven't had a chance to revisit the error I found in the notes yet. I have been distracted by a multitude of silly things in the last day, and I will eventually get back to that error and fix it. Now, I did post an announcement with my old course notes, which have the correct formulas because they're taken from Thomas's calculus, and we can be sure those are correct. All right, but in any event, so here's an example. Let's see, given f equal to this is a good one, x, y, z. All right, you've got here all right. So here I'm talking about the cube, which is minus 1 to 1 cubed. All right, so it's the cube, which, you know, the side length of the cube is what? Like, okay, this point here would be 1, 1, 1. This point down here would be 1, 1, minus 1. All right? Then, my question is, what is the flux of this vector field through this particular region? What's the flux through that particular patch? And I'm assuming it's like a quarter of that face, yeah? So what do you guys think? First of all, what's the way not to do this? Like, I'll tell you the way not to do this is just to do it directly, right? For sure, parameterizing this little patch and like calculating the integral directly, it would be unpleasant. I guess it wouldn't be too bad. I mean, we could do that. I guess that might even be instructive, but there's an easier way, which is what? The divergence theorem, right? So the integral through the boundary of the whole cube of f dot dr, right, is equal to the triple integral over the cube of the divergence of f, integrated over the volume, right? And so what is that? How does that help? All right. So there's various ways to go about this, but I'd like to point out something by symmetry. This is equal to what? How many times the flux in that quarter face must the total flux be? And what's the symmetry I'm exploiting? I heard a 24. Do you guys agree with that? I agree with that. 24, because there are 24 quarter faces in the whole cube. There are 24 quarter faces in the totality of the cube, right? And the thing is, this vector field, as we have talked about before, is really rho hat, which is manifestly spherically symmetric, right? It's the same in all different directions. If you like, another way to see it directly, and even in terms of the Cartesian variables, is there's an x, y, z interchange symmetry here, right? It's like the x is to x, y is to y, z is to z. It's you know, it has this symmetry. I'm being a little bit vague about how we define symmetry, aren't I? And that's okay, because that's how we do. But the thing is, this cube, it also has that same, you know, there's no respecting of x or y or z with this cube, is there? It sees all three dimensions as the same, and so we can expect that nothing should distinguish the flux through one of the 6 faces with any of the other 6, and likewise, any of the quarter faces are equally symmetric with respect to this vector field, right? Does that make sense? So that's 24 times what we're interested in. On the flip side, the divergence of this is, well, 3, right? And this is, what's the side length of this cube? 2. So the answer is 3 times 8, I guess, because 2 cubed is 8, which is 24. Oh, weird. So the flux is actually 1. As I've set this up, the flux is one unit of flux. All right. Now, what are the actual units for flux? Well, that depends on the physical application, right? If you're working with an electric field, it has to do with the units which go with an electric field. If you're working with a magnetic field, it has to do with the units that go with a magnetic field. If you're working with a force field, it has to do with, well, the units that go with force, right? And so forth. But we just work with pure numbers in here. Any questions? All right, well, let me move on here then. So one of the major reasons that we're studying vector calculus in this course is that it has vast and interesting application to physics. And I should talk about that a little bit more here. So let's talk about physics a bit. I'll eventually get back to math proofs and stuff, but you know, let's do some physics here. So electrostatics, electromagnetism. Let's talk about this. What is electromagnetism? Electromagnetism is defined essentially as being the study of these 4 partial differential equations. Now, I'm going to use physics notation because, well, I have to. Otherwise, but you should understand the context here is that the rho is not the spherical radius here. It is what? So to be clear, here rho is equal to dq dv. It's the volume charge density. All right? So for instance, if I was to integrate, right? If I was to integrate rho dv, what would that give me over some volume E? What would this give me? It would give me the charge enclosed, right? This is the charge inside E, right? Now J is a little weirder. J is what's known as the current density. It's the current per unit area. So J here is equal to a current density. So like if I do the current enclosed, I could do, say, the integral over S. It's a double integral, actually, of J dot ds. So this would be the current flowing through S. All right, so that's what's going on here. We have charge density and we have current density. These are part of what make up Maxwell's equations. Now, the epsilon naught and the mu naught are particular constants. Epsilon naught is the so-called permittivity of space, and mu naught is the so-called permeability. And I say space. Now, it just so happens that if you do, for example, the speed of light is like 1 over the square root of mu naught epsilon naught. That's one way you can understand these constants. They're connected to the speed of light like that. I talked about this the other day. I showed you guys that we can derive wave equations for the electric and magnetic fields in the absence of sources. We derive that the electric and magnetic field satisfy what are known as wave equations, with the speed of light being their speed. Okay, so these are Maxwell's equations. Now, these are not the Maxwell's equations that you typically see in physics 232. In physics 232, usually, we take a more integral approach, right? So like, example 2, if I have, for instance, this, say, sphere, and I've got a charge in the middle of it, all right? Then we think of what's called a Gaussian sphere. All right? And so, all right. Gauss's law in differential form says that the divergence of the electric field is equal to the charge density divided by epsilon naught. All right? What happens if we integrate that over, the ball? So this is the boundary of the Gaussian ball. No one ever calls it a Gaussian ball. I'm just doing it now, so you'll forgive me. But it is what it is. I really need to find a better name for this. Let's call this thing B. And let's call it B sub r. And let's call this thing S sub r, because I just want to think about like spheres. So if I integrate the divergence of the electric field over the volume, well, that's the equal to the, I pull the epsilon naught, it's constant, pull it out, rho dV over the ball, all right? Now, I've drawn the picture as if there's just a point charge at the center of the ball, but like in principle, it could be more interesting than that. Like this Gauss law is general, all right? It's like always true. And so, well, the divergence theorem says what about the integral of the divergence? We get what? This is straight up equal to the surface integral over the boundary of the ball of E dot ds, right? This is the divergence theorem. Now, if you've been paying attention, you might be a little bit bothered by that because I got done telling you about like the electric field from a point charge being divergent at the origin. So in order to make us feel better about that, let's suppose it's not a point charge. Let's suppose it's like smeared out over a nice little spherical ball. Now there's no divergence. If we just smear the charge out a bit, the divergence doesn't go to infinity. So anyway, Gauss's theorem gives me, or the divergence theorem gives me this. But on the flip side, what is this? Well, this is 1 over epsilon naught times the charge enclosed, right? You should recognize that as Gauss's law from physics 232. The flux, the electric flux, is equal to the charge enclosed divided by the permittivity of free space. Now, the way we use this in physics 232 typically is we apply Gauss's law to some sort of shape which has a really nice symmetry. Yeah.
Like problems have to do with like electromagnetism and stuff like that.
Sure.
Like
I could do that. Yeah. Let's see here. I mean, I'm talking about. I mean, I think it's part of the course. So yeah. I mean, I usually set it up as a math problem, but I think we can understand this. So the thing is, if the charge distribution is spherically symmetric, then what does that say about the flux here? So if this is, if the charge distribution is spherically symmetric, all right, that's a key proviso here. Then the electric flux can be written as 4 pi r squared times the magnitude of the electric field, right? Now, if the charge distribution is not spherically symmetric, I can't do that, right? I can't do that in my, for example, if you change this F to an E in my example 1, like we could not just say, well, first of all, I mean, where would you put the Gaussian sphere in example 1? But like I couldn't do this in example 1 because example 1 didn't have a spherical symmetry. for the I'm talking about the I'm talking about the cube. I couldn't do it for the cube, all right, because the cube doesn't have the spherical symmetry directly. Like the magnitude, the magnitude of the electric field on that cube, it would be a complicated function of the point that you were on the face. Here, on the other hand, every point on the Gaussian sphere has the same distance from the origin, and so I can assume that the magnitude of the electric field is the same over the whole sphere by the symmetry here. But it's also equal to q over epsilon naught. So lo and behold, we find the magnitude of the electric field is q over 4 pi epsilon naught, 1 over r squared. And so this right here, of course, is that's Coulomb's law, right? And so what I'm showing you is Gauss's law implies Coulomb's law, actually. We can see this if we are willing to make a little symmetry argument. Now, there are other examples which have different symmetry, like another good example is if you have like lambda is dq dz, so this is a like infinite line charge. In this case, so like the way the electric field works is it always points away from positive charge, right? It points away from positive charge. And so as we envision the electric field around this infinite line charge, it's going to be like, it's easier for me to picture it if I look at it dead on like this, all right? So the electric field, it goes like this, all right? This is the way it works. And the same in all directions, all right? This is the deal. I think that's enough, right? So no direction is preferred, right? Okay, like so it's like it goes out like that. So if this is the z-axis, you can kind of tell me what the general direction of the electric field is. What it's like the magnitude. What is this radially outward? It's r hat, right? That would be how the electric field goes out from that positive line charge. In this case, if we want to use Gauss's law to figure out how the magnitude of the electric field works, the appropriate thing to use would be a cylinder, because this problem has a cylindrical symmetry. So what you do is you think about putting a little what's called Gaussian cylinder here, like this, and we'll make it go, length L, and we'll let it go out here to radius r this time. And so as you picture this, the electric field, right, it's going like this here, right? But down here, if we look here and if we look there, what can you say about both of these? No flux there, right? Because at the caps to this Gaussian cylinder, the electric field is not cutting through the caps. It's just tangent to the caps, so there's no flux there. All right, so again, we basically take the triple integral of the divergence of the electric field over the volume. This case, I'm going to need to give this name. I guess I'll call it E again, just to be boring. Integral over the volume E. So that's of course, the double integral of the boundary of the volume E dot ds, right? Now, this is also equal to the triple integral by Gauss's law in differential form of rho over epsilon dv, right? Which is just the charge enclosed divided by epsilon naught. But what is that here? What is the charge enclosed as you look at this particular example? I'm assuming a uniform charge density, right? So you go from this point up to this point. This right here, this region right here, see this? This is where we have to figure out charge enclosed from. So like the charge enclosed, we can, if it's uniform, we just need to take like lambda times the change in z. What's the change in z here? It's just by our construction L, right? So like the charge enclosed would just be L times delta z in this particular example. My bad. L. Oh, what's L? Listen to me. Lambda. What? My change in z is. Sorry, my brain is not working. So lambda times change in. Good goodness gracious. Lambda times L, charge enclosed. All right, finally. So lambda L over epsilon naught, that's my charge enclosed. But you see the flux here is a little bit more interesting than the sphere. It's not the totality of the surface that matters. It's just the side of the cylinder that gives us flux, right? So we have the integral over the side of E dot, well, it's r hat ds, isn't it? Yeah? And so that works out to, by the cylindrical symmetry, the magnitude of the electric field times the surface area of the cylinder. What is the surface area of a cylinder? Yeah, 2 pi big R in our current context, right? 2 pi RL, all right? And so we have this equals that. That gives us what? Thus, the electric field magnitude is lambda over 2 pi epsilon naught times 1 over big R. And so what that shows us, if we think about arbitrary radius, the electric field is like lambda over 2 pi epsilon naught r hat over R. So this is how the electric field works for an infinite line charge. If I had done that kind of last finishing step in the previous example, we would have found that the magnitude of the electric field here is actually, q over 4 pi epsilon naught, in our notation, rho hat over rho squared, right? My apology that we're doing double duty there on the rho, right? We're using it for both charge density and the spherical radius. I hope you can forgive me for that. So, any questions? So these are the two probably most interesting, non-trivial examples of flux integrals that you'll come across in Physics 232 that meaningfully interact with this course. That you really couldn't set up the honest-to-goodness flux integral over a sphere or a cylinder without having this course, right? That's pretty much well outside the realm of Calc 1 or 2, truthfully. Yeah? But you also see here that you don't actually end up needing to use the definition of flux to actually do these problems, do you? Because symmetry is the hero, and symmetry gets us around the problem of actually directly calculating the flux because the divergence theorem converts it to just finding the charge enclosed. That's really beautiful, actually. So, all right, that's Gauss's law. Ampere's law, right, comes from this animal over here. And let me do an example of those. I guess I should do it over here. Example 3. This is called Ampere's law. So assume that the current is steady. For physical reasons, that implies that the partial E partial T is equal to 0. And so in that context, we just have the curl of the magnetic field is equal to mu naught J. So this is what's known as Ampere's law. The partial E partial T term is known as Maxwell's correction. If you go back to the previous class I talked about these, you could see there, if you study it, that Maxwell's correction, the term that we're neglecting here, is actually responsible for the wave equations working out as they do, which is the really interesting part. Now here, so what we're going to do is we're going to, we think about a long steady current, all right? So here's the current. It's going like this. So current is charge per unit time flowing like through a wire, right? If you were to put a gate here and to count charges passing, that per unit time is what we call current, right? Current is charge flowing in a direction. And so what Ampere's law says is that if you have a long steady current, well, it doesn't have to be long, I guess, but if you have a current, which is steady, you can look at what's called an Amperian loop. And so like here, I'll just do a circle like this, all right? Radius r. This is known as an Amperian loop. The concept of an Amperian loop, much like the concept of a Gaussian surface, they're not actual physical surfaces in the sense of like your skin, right? It's a mathematical construction that allows us to determine the values of the electric or magnetic field in this case. So this is an Amperian loop. It's not an actual physical loop. It's a mathematical loop that we use to figure out the magnetic field. And so here's the deal here. We take the integral, let me call this loop, CR, all right? That's, by the way, the boundary of dr, where I'm taking dr to be, well, we'll talk about that in a second here. So we have the integral over CR of B dot dr. Right, I want to calculate the circulation of the magnetic field. Now, all right, so truth in advertising here. The magnetic field, if it's coming out at us, I draw what? Like this symbol, right? It's like an arrow. This is the magnetic field. Not the magnetic field, this is the current, my bad. So if the current is coming out at us, right? The right-hand rule tells you how the magnetic field works. The magnetic field of a current, it encircles the current typically, except when it doesn't. But most textbooks tell you that magnetic field lines always form closed loops, so it must be true, right? It's not true. But so this is the way the magnetic field lines loop. They encircle the current. So I expect that by the symmetry of this very long current, that this circulation I should just be able to get by symmetry here as being equal to, 2 pi r times the magnitude of the magnetic field. All right. So by the way, that's what we have to look forward to there. But we know other things. We know that this Amperian loop we can view as the boundary of a disk of radius r, right? Like we can look at this bounding disk right here. Yeah? Like that. And we can use Stokes' theorem, right? So this is the double integral over the disk of radius r, right? Of the curl of the magnetic field. Yeah? And what can you tell me about that? Well, if you believe Ampere's law, you can tell me, well, that's actually what? That's actually, we can pull the mu naught out. That's actually mu naught times the double integral over the disk of radius r of j dot dA. Well, ds rather, my notation here. Some people use a dA vector rather than a ds vector for the area element. Like the ds vector is not written in stone. Different books use different notation. If you look at higher level material, you'll find that they don't write 2 integrals for the double integral, and they don't write 3 integrals for the triple integral. They write a simple integral because context will suffice to tell you whether it's a double, a triple, or a single integral. But I write the double and the triple here because I want you guys to make sure you understand what you're doing. All right, so what is this? I told you over here what that was, right? That was the current enclosed by the surface. What's the current enclosed by this surface? Well, I told you there's just one long steady line current going up the z-axis basically, right? So the answer here is mu naught times I. And so this gives us that the magnitude of the magnetic field is mu naught I divided by 2 pi r, right? And so if we put in the direction, the magnetic field, it wraps like this, right? What is this thing that encircles the z-axis like this in the counterclockwise sense? We have a name for this. This is what? magnitude of B times theta hat. That's theta hat. That's what that is. So we have mu naught I over 2 pi r. Well, let me use little r times theta hat. There you go. This is the magnetic field due to a long, steady current. All right. Now, we do much more than that, of course, in Physics 232, but this is the basic example, and I want you to see that Stokes' theorem is the hero here, right? Stokes' theorem is what allows us to connect this basic local statement of electromagnetism with this integral statement of electromagnetism. Stokes' theorem and the divergence theorem connect the partial differential equations, which are actually basic to the theory, with the integral formulations of the law, which you tend to see in Physics 232. All right? Now this one here, this one here, the curl of the electric field is minus partial B partial T. Do you guys know what that one's called? That will be our final example for all this. This guy's what? This is known as Faraday's law. Now this is Faraday's law in differential form. There I should probably introduce for you guys the concept of voltage. All right? You guys heard of voltage? I hope. Maybe. It should not be too shocking to you. I'm sorry, that was horrible. No, I regret nothing. I regret nothing. How many 6/7s do you think are on my 221 test today? A lot? Yeah. All of them? No, I haven't achieved that yet. I'm not there. That level of frivolity is not. It's outside my grasp at the moment. But so, what's that?
I think you should do that for our final.
Do that for your final? Okay. Yeah. So, like, basically here, for the Faraday's law, if we just imagine some kind of, surface, S, right? And so I'm supposing, it's got some normal direction, let's say, right? So then the boundary of S is oriented which way? Yeah, counterclockwise. So like that, right? So we can calculate the flux of the curl of the electric field over this thing, right? And that would be equal to the integral of the minus, I'll put the minus out, the flux of the time derivative of the magnetic field. Now that's wild. We haven't really done much with time dependence in here, have we? That's something you're going to have to face as you apply Calculus 3 to actual real world problems, is oftentimes time dependence matters. Where's the time dependence in most of what we do? We deal, if you maybe take this for granted, but we deal with static vector fields in here for the most part. Yeah? Anyway, so that's just, I'm just saying the flux of this is equal to the flux of that. That's assuming that the physical law holds, Faraday's law. But of course, Stokes' theorem gives me that this is the integral over the boundary of the electric field dot dr, right, is equal to, well, we can pull the time derivative out, partial t. Actually, when I pull the time derivative out, well, fine, I'll just leave it like that. And then we have double integral over s of b dot ds. What is that, though? Can you guys tell me in words? If B is the magnetic field, what's the double integral over S, like this, of the magnetic field? That would be what we would call what? What I just boxed it in green. What would that be? That would be the magnetic flux, right? The magnetic flux. So what we're looking at here actually is minus the derivative of the magnetic flux with respect to time. And I can trade this the partial derivative for a total derivative, because if you think about it, the flux is just a function of time. So whatever spatial dependence there was on B, that's gone because it's been integrated out. So it's a total derivative, in fact. And so this, but what's this? So that begs the, I mean, this is the other thing I need to tell you guys about, but the electric field, right, is minus the gradient of the voltage function. So this is electric field is, you know, minus the gradient of voltage, or potential. Potential is potential energy per unit charge. Now, well, fine. All right, truth in advertising here, technically speaking, and with writing this, I have firmly left the shores of physics 232, because what I'm about to write is not a physics 232 thing. But technically speaking, there's also minus partial a partial t. And that is a new thing that you would study in physics 331 if you were to take it here. But this right here, I'll talk about this more in a second. This is the so-called vector potential. So generally speaking, the electric field is not just the gradient of the voltage functions, it's also you have to subtract the time derivative of the vector potential. But anyway, that said, what you're looking at here is the integral over the boundary of S of, you know, well, anyway, let me get to the point. The point is that this is the EMF. It's the change in voltage over the loop. So this is Faraday's law. It says that the voltage induced around a loop by a changing magnetic flux is proportional to the rate of change of the magnetic flux. And you can kind of see that from this, but I mean, there's a larger point here. This electric field, is it a conservative electric field? I mean, it cannot be conservative, right? Because we're saying the integral of the electric field around a loop is non-zero. So there's, at the start of physics 232, you talk about electrostatics. In electrostatics, the electric fields are conservative. This term is actually not present. All right, but if that term is present, that partial a partial t term is actually present and non-trivial, that can spoil the conservative aspect of the electric field. It's an induced electric field. Induced electric fields do not have to be, in fact, they aren't conservative. But anyway, so there you go. That's like a, I hope you can see that in order to understand electromagnetism properly, we have to apply Stokes and Divergence theorem, right? It's all that. All right. So let me. Any questions? No. All right. So just a reminder, we're collecting the remaining, the ones I've published at least, the surprise technician, those two I'll collect Thursday. And of course the mission I collect tomorrow. Now I will hopefully write a few more surprise technicians, and you'd like for that to happen, right? Because at the end of the day, I'm dropping the lowest scores, right? So everyone I offer past this point is an opportunity to erase a bad score earlier with a better score, right? And so just that's something, if you have time, I would suggest, trying to erase the bad score, right? That's just in your interest, right? But I haven't written more past the ones that you guys already have yet. So, but I will. So I was just talking about the potential formulation of the electric and magnetic field. I'll talk just a little bit about this, not too long. I already kind of spilled the beans here. The electric field is minus the gradient of the voltage function minus partial A partial T. Well, this A that I've introduced is actually the curl of A is the magnetic field. Now this, again, admittedly, we do not cover in Physics 232. Typically, I don't know, maybe Dr. Bujaras does. He's a little bit crazy sometimes. He's good people. But I know Professor Dromby will not, because this is not in the standard material. But anyway, so this is the so-called vector potential. It's kind of, well, I've worked some of these problems for you, right? I've asked you to find a vector potential, actually, for various forces, haven't I? Think back to your homework. I said, find a vector field whose curl is another vector field, right? I was actually getting you to find a vector potential for that vector field. So, all right, so like, usually, partial A partial T is equal to 0. This would be for electrostatics and also magnetostatics. So in electrostatics and magnetostatics is when the currents involved are steady, all right? In a nutshell, the divergence of the current is equal to 0. This is what we mean by steady current. Right. Some people say constant current, but that that kind of is an annoying thing to say, because if you're talking about current, there's charge flowing. How can it be constant? You know, I mean, it's, well, anyway, whatever. But okay, so like example 5. I think you guys can all do this one. So suppose you have the electric field. And I think I've talked about this before, but I'll talk about it again here. You know, we got rho hat over rho squared. You want to say that's minus the gradient of some voltage function. How do you find the vector? How do you find the potential here? So we're going to assume that the partial A partial T thing is 0, because that's not for this course. I'm just mentioning that because there's an error in my notes. I have a plus here at one point in the notes. That should be corrected. Anyway, so can you guys tell me, how would you suggest we solve that? I would strongly recommend using like the gradient in spherical coordinates, right? We have that this is what, like minus rho hat, partial v, partial rho, right? And then plus other terms, right? I mean, I guess we could write them down. What are, you guys have to help me out. I forget the other ones, but I think it's 1 over, is it 1 over rho? Partial v, partial phi hat, plus 1 over rho sine phi maybe, partial v, partial theta hat. Do I have it? I think that's it. The point is, these are 0, right? So you pretty much disregard those. And to find the voltage with this formalism, all we have to do is try to solve minus 1 over rho squared equals to partial v partial rho, right? Can you guys do that? Integrate both sides. What do you get? Which function, if I differentiate, I get minus 1 over rho squared? 1 over rho. Rho. So there you go. This is the so-called Coulomb potential. It's the potential whose gradient times minus 1 gives you the electric field due to a point charge. Simply reciprocal from the distance. All right. What if we were looking at the line charge? That one we had what? We had lambda. I'll put the units in this time to make it more fancy. Lambda over 2 pi epsilon naught r hat over r. Suppose I want to find that's minus gradient of v. What should I do to find the potential here for this one? What would you guys suggest? What's that? I should not use the spherical gradient this time, right? I should use the what? Oh, right. So minus, let me put the minus on the other side, because that's less weird. So the gradient is, I think we got partial v, partial r hat, plus 1 over r, partial v, partial r, theta hat, plus partial v, partial z, z hat, right? That's the general gradient in cylindrical coordinates. Only 1/3 of that actually mattered, right? Like this right here, we want that to be 0, right? So it suffices for us to simply solve what? We just need to solve, partial v, partial r equal to what? Minus, minus lambda over, I put the dimensional constants in this time just to make it look fancier. So minus lambda, all right, so what do we got? We got v equal to what? Natural log r, right, so I got minus lambda over 2 pi epsilon naught, the natural log of r, and then of course we can leave it like this, yeah? If you like. You can add a constant to it if you prefer, right? Whenever we're integrating, we always have freedom to add a constant, right? That corresponds to our freedom to set the potential energy per unit charge to be 0 where we like. Now, some of you guys are electrical engineers. Oftentimes you don't have this freedom because the ground is stated, the place where voltage 0 is given to you. So you have to adhere to that boundary condition. But yeah, there you go. This would be the voltage for an infinite line charge. This all becomes much more difficult if we use Cartesian coordinates. Yeah? All right, so now let me ask you a really perverse question. Question. Let me put it in the middle. So I'm gonna throw this question out here. I'm not gonna answer it, but I'm gonna put it out here and see if you guys can think about it. This is a hard question. I've asked this on an upper level class and had nobody answer it. I know the answer to it. I know many answers actually at this point, but I don't think any of them are particularly obvious. If we think about the vector field F equal to x, y, z divided by x squared plus y squared plus z squared to the 3/2 power, right? AKA rho hat over rho squared, right? Also known as rho hat over rho squared. This is the inverse square force field. Can you find a vector potential for this? Can you find a vector potential for this? Now, let me give you a cautionary calculation. Suppose you could, right? This, again, is in spherical coordinates, rho hat over rho squared, right? And so if we integrate that over the sphere, what happens? I should probably do more examples because I just keep doing this example, right? but anyway, if we integrate over the sphere of radius r, the Coulomb field, this thing, rho hat over rho squared dot ds, right? That's equal to, as you guys know, 0 to 2 pi, 0 to pi, rho hat over r squared. What's ds for the sphere? We worked it out. It's r squared sine phi rho hat. You know, this, my bad. Come on. Dot rho hat r squared sine phi d theta, right? Rho hat dot rho hat gives us 1. The r squareds be canceling. And we've got integral from 0 to 2 pi of d theta, integral from 0 to pi of sine phi d phi. All right, so great. This is 4 pi. The flux of the unadorned Coulomb field is 4 pi, the unit charge field. But on the flip side, we can look at this. All right, so suppose that you've got a vector potential, yeah? What would that mean? I can replace A with the curl. I mean, I can replace F with the curl of A, right? And then what could I do? I've showed you two different arguments, right? Its sphere is a closed surface. We could go to the top cap and the bottom cap and apply Stokes' theorem separately there, and show that it's 0 by a double application of Stokes' theorem on the northern and southern hemispheres. I prefer to use the divergence theorem, right? The divergence theorem says this is what? The triple integral of the boundary, or the ball radius r, of the divergence of the curl of A, right? Which would seem to be 0, right? Now, you'd be like, but you're being sloppy there because we know that the field is divergent at the origin. So, maybe this is just because you've thrown in the divergence at the origin, you're getting this contradiction. And well, maybe it is. I mean, it is partly that, for sure. So this maybe would seem to throw cold water on your ability to find a vector field whose curl is the Coulomb field. But I'm telling you that you can do it. You just can't do it for the whole sphere. So see if you can find it. Try it out. So that's a problem I wanted just to throw out there. See if you could find that. All right. So let me wrap up this physics stuff. There's a deep theorem in the notes. I don't want to go through the proof with you guys too carefully in here because you guys are seemingly growing impatient with my physical musings. So I best draw it to a close. But there is one other thing that we should talk at least a bit about, which is the fact that if we have Gauss's law, right, is this. All right. And then in the context of electrostatics, we're trying to solve the electric field is minus the gradient of the voltage function, right? This is electrostatics. So there's no vector potential derivative term there. Then if I plug that up in here, I get the divergence of minus the gradient of the voltage is equal to rho over epsilon naught. This can be rewritten as so-called nabla squared. V equals to minus rho over epsilon naught. This is known as Poisson's equation. If rho is equal to 0, you get nabla squared V, which by the way is just like Vxx plus Vyy plus Vzz equals to 0. This is Laplace's equation. And of course, there are also two-dimensional versions of it. So like the voltage function, for example, has to solve Laplace's equation in the absence of charge. In the absence of charge, you have to solve Laplace's equation. And like there's a vast amount of mathematics which is known for solving Laplace's equation. It turns out we can derive a general solution to Poisson's equation using slight extensions of like Stokes and the divergence theorem. So these are known as Green's second and third theorem and such. But yeah, I don't feel like doing it today, actually. Any questions? I'm gonna save it for another day, I think. This is sort of towards the end of my notes, as I have a derivation of this. All right, well, I think I'm going to stop here today, actually. There aren't any questions. So I would encourage you guys, talk amongst yourselves and figure out